So we will pass on to finding out the moment of inertia of some regular bodies. So we will start with the one-dimensional body, which would be a thin rod, uniform rod. So this is a rod. It's not a rod. I asked you to consider this as a uniform rod. So what will be the moment of inertia if I'm going to suspend it from the center? And how would the moment of inertia vary if I'm going to suspend it from one of the sides? That is what we are going to see today. So let us go into discussing the moment of inertia of a uniform rod. So we'll be seeing a series, moment of inertia, and they are all labeled as moment of inertia as continuous bodies. So we shall be starting with moment of inertia of a uniform rod. So this is my rod of length L. For convenience purposes, I'm taking the center to be 0, this side as minus L by 2 and this side as L by 2. So let me say this rod has a mass M. Okay, so mass per unit length of the rod, which I am going to call M, is equal to M by L. That is the first point. Now I am going to consider a small element dx, thickness dx at a length, at a distance x from the center. So mass of the element dx is equal to the entire mass, which is going to my entire mass per unit length m into dx. So now what I need to find out is moment of inertia of the element dx. So let me just say moment of inertia of dx. You know, moment of inertia is equal to mass, which is m into dx, into square of the distance. The distance here is x. So square of the distance is going to be x square. So you have to write m x square into dx. This is the moment of inertia of this tiny element dx. But I need to find out the moment of inertia of the entire rod, which is actually made up of tiny parts like this dx. Okay, so I actually cannot cut, so which means I have to integrate. So moment of inertia of the rod should be equal to integral m x square dx. And what would be the limit? The limit would be, please tell me, the limit would be minus L by 2 to plus L by 2, as you can guess. The limit would be minus L by 2 to plus, minus L by 2 to plus L by 2. Now let us integrate this. M is a constant, you can take that out. So you will have x cubed by 3 within limits minus L by 2 to plus L by 2. So I can write here M by 3, I can bring this 3 outside, L by 2 the whole cube minus L by 2 the whole cube. So what will I get here? So I will get here m by 3 L cube by 8 plus L cube by 8. So what will I get here again? M by 3 into 2 L cube by 8. So let me complete it in this page itself. So what will I get here? So the moment of inertia is equal to m by 3 L square by 4, because this 2 and 8 will get cancelled here. I can rewrite this as ml L square by 12. What is this ml? I see m is equal to m by L, or capital M is equal to ml. So I can write moment of inertia is equal to m L square by 12. So this is the moment of inertia of the rod when the axis is taken through the center of the rod, the common case. Now let me take a new case, the same rod, which is of length L. Okay, I have the center at 0, and I'm now taking the axis at some point P, which is passing through the corner of the rod. So which means the distance between the center to this is, distance between center to this point is L by 2. So moment of inertia at P can be given by using parallel axis theorem. Moment of inertia through the central axis, what is that? M L square by 12. So we'll have M L square by 12 plus mass into square of the distance from the center. What is the square the distance from the center? It is L by 2. Square of the distance will give you L by 2, the whole square. So you will get M L square by 12 plus M L square by 4. Obviously, you can take LCM plus 12 M L square plus 3 M L square. So this would finally become equal to 4 M L square by 12, or moment of inertia at P will be equal to M L square by 3. So this would be the moment of inertia when you are not taking the axis through the center, but through a parallel axis at a distance L by 2. The other cases we'll discuss in the next class.